since we want to find the acceleration, you know that in physics we have to apply the methodology to find the acceleration using dynamics, which is first you set up. Second, you draw the forces acting on the object. This is the object. What forces are acting on the object? And in which direction? Gravity. Everybody can see that gravity is there? Gravity. Gravity down to the center of the earth. What else? Friction. In which direction? Backward. So the friction is backward. The friction, I will explain carefully because the friction has a certain detail that is very important here. And then normal force. These are the forces, and these are the forces from the point of application. You can see that. Okay, this is the row diagram. The free body diagram will be the same, like this, like this. So here Fg, here normal force, here friction. The friction is static, not kinetic. Why static? Even that the object is moving, the friction is static, and this is the main detail.
It's not sliding.
Here.
It's not sliding.
It's not sliding, or it's not slipping. It's not slipping. When you see that an object is rotating but it's slipping, there will be kinetic friction. The friction here every time, what it's doing is just creating the torque. So you can see that the friction at this point is just creating the torque, but you can see that the friction is acting and it's static. It's only acting at one point and it's static. And this is the main detail here. Why the main detail? Because the friction is static. What will be the work done by the friction? What is the definition of work? Work is the force times the displacement times the cosine of the angle. But if there is no displacement, what will be the work done by the friction? Zero. Means that there is no energy lost due to the friction. And this is very important. Since there is no energy lost due to the friction, is there any non-conservative force here? There is only conservative force. And if there is only conservative force, which theorem of the three we use? First, second, or third? The third. EI is equal to final. And this is the key when we will use energy here. No energy lost due to the friction if there is no slippage. Knowing that, this is for when we will do energy perspective. When we will solve the problem for energy perspective, we will keep that in effect. Okay, but let's start with the Newton laws. Once we have the free body diagram, this is the x coordinate, which is Fgx. Everybody knows that this is mg sine theta. And this is mg cosine theta. That's it. This is my free body diagram. Newton laws. So if we apply the Newton laws to the center of mass, the center of mass is rotating or translating? Translating. If it's translating, which Newton law you apply to a translational motion? Sigma F equal to ma. Mass of the object time acceleration. All other particles are rotating with respect to the center of mass. All other particles rotate with respect to the center of mass. So to all other particles, we need to apply sigma tau equal I alpha. And these are the two Newton laws. Then, the next step is to disclose what are the net forces acting on the object. This is for the center of mass. We omit the free body diagram for the other particles rotating. So for the other particles, the only thing we need to know that we have on the poly acting the friction. Since this is acting here at the center of mass, it's not acting on all other particles. The gravity is not acting on other particles, which was the examples that I gave the other day, that you can see that if I throw this like this, the gravity doesn't make it to rotate this anymore. It will go like this. You can see that the gravity acts in the center of mass and always go in the same way. Why? Because the gravity doesn't act in all other particles, act in the center of mass. So it doesn't make to rotate. The same here. Gravity acts on the center of mass. Then the one that making able to rotate the body, which force will be? Which force is the one that makes able to rotate?
Friction.
The friction. So the friction is creating the torque. And the normal force acts from here, but remember, the normal force, since the normal force is perpendicular, what will be the torque? By perpendicular to the surface, right? Like this. So it's parallel to the radius. Is that correct? Is the normal force parallel to the radius? So if it's parallel to the radius, when we go to this formula for torque, the formula for torque here, since this, the angle between R and the normal force, they are parallel, what will be sine of 0 degree? So, makes any torque? No torque. So what is the only force that creates torque? Friction. So, in this case, what will be? What are the forces acting on the center of mass? The friction, remember, will act all over the place. So the friction is acting also because it's retarding the motion. So we have mg sine theta minus friction equal to ma. That's the translational motion equation, which is consistent with my free body diagram. Mg sine theta minus the friction equal to ma. Then we go to the equation for torque, and we said that the only force creating torque is the friction. So it will be only frictional torque. But we need to know the direction.